I need to introduce probability because it's an important part of data handling and also dealing with complex problems in biology. So at the end of this class, you're going to be able to describe when we need to use probability and describe the basic rules of probability and calculate the probabilities of simple events. So we use probability when we have incomplete knowledge. When you have something that's complicated. You use probability when you don't know absolutely that something's going to happen. So for example, we use probability in assessing how likely you are to have a virus like COVID. We use it in complex systems like the weather. We use it for predicting risk. And we use it in games and when there's a chance, when chance plays a role, like in throwing a die, flipping a coin. And we also use it when we know something about frequencies within a population, but we don't know about the specifics of that individual. So if you think about probability in biology, in the woodlice experiment, depending on the day of the week and who does it and how long you leave the woodlice there, and just a set of luck, depends on how they'll be distributed between the 4 different chambers in the choice chamber. When you're looking at entire populations, then that's the process which is called epidemiology. And at the minute you're seeing lots of epidemiology going on about COVID and predictions about how many people are going to be infected and infections and mortality rates. If you do genetics, then we know that there are different variants within the population, but we don't know which specific variant any particular individual has. So we can work out the probability of them having that variant. Now, eventually, if you can be bothered and do the entire genetic sequencing of everyone, then you can actually work out the exact answers and you don't need to use probability anymore. And the final case we're going to use probability is the fabled p-value for assessing probabilities. For assessing hypotheses. But we'll come back to that later when we go to study hypothesis testing. An event is something that can happen. So the exhaustive set of events is all the possible things that can happen. So on a die, there has to be a number. If it's a not regular 6-sided die, then there are 6 numbers. You can have a cheating die where 2 of the numbers are the same, but still there are 6 faces of the die and any of those 6 faces are equally likely to turn up. Similarly, a team that is in the Premiership has to win the Premiership. Now it could be Arsenal, so you can work out their probability of winning. Now, given their existing form, that probability is not going to be that close to 1, but somebody's going to win it. Somebody's the most likely team. So events are a set of alternatives. They're the things that can happen. So Liverpool winning, Chelsea winning, Arsenal winning, any of the teams winning, Leicester winning. So the simplest way of calculating possibilities is if all the events are equally likely. Then you just count up how many alternatives you have and then divide 1 by those number of alternatives to work out the probability of each one of the alternatives occurring. Now the real problem in biology is not all of the possibilities are equally likely, and sometimes we don't know what the differences are between the probabilities. One thing we always do know is the total probability is always 1. Something has to happen. If I exhaustively look at all of the different possible events, then one of them has to turn up. If I roll a die, I have to get a number. If I pick a card, I have a card. If I live, I have a gene. I don't know which variant of that gene I have, but I know I've got one, because otherwise I wouldn't be alive. So what I'm going to do here is visualize probability as an area. So I'm going to imagine that the screen, a sheet of paper, this lecture slide, is the event space, is all the possible events that could occur. So what you're going to do is then assign areas on the screen describing the different events that could happen, and that will occupy a fraction of the area, a percentage of the area. I shouldn't really have mentioned percentages here because I want you to try and avoid using percentages to describe probabilities if you can. This is because a percentage will give you a number between 0 and 100, and a probability I want to be a number between 0 and 1. That's because otherwise when I mark my assessments, if you've written them as percentages, you'll probably get them wrong. So here is using that area concept to represent a flip of a coin. All coins are fair. It's almost impossible to get an unfair coin. Painting on one side, doing whatever you like, they still, when they're flipped, will come down on average 50% heads, 50% tails. So in this case, the area is 1 to 1. They have equal area out of the entire area of the slide. This is the area for rolling a die. So I've split the area of the slide into 6 equal sections. Now the reason for splitting the section for 2 into 2 different areas is to show the only thing that matters is the area. It doesn't matter where it is on the sheet, it just matters the size, the area that it takes up. So in this case, you're equally likely to get any of the 6 numbers from 1 to 6. And if I close my eyes and threw a darts at the screen, which wouldn't be good for my computer, then I'm going to get exactly the same distribution of numbers as I would get if I actually rolled the die.